Imagine you run a cozy coffee shop that sells just two drinks, lattes and cappuccinos. Every morning, you've got limited milk and limited barista time before the rush. The big question is how many of each drink can you make without running out of resources? This is where systems of inequalities come in. They let us try the limit as equations or inequalities, then find all the possible drink combinations that work. Let's say in a coffee shop, each latte needs 2 cups of milk and 3 minutes of barista time. Each cappuccino needs 1 cup of milk and 4 minutes to make. You only have 18 cups of milk and 48 minutes before the rush is over. Let's say X to be the number of lattes and Y the number of cappuccinos. We can translate these into inequalities. Since making X lattes uses 2x cups of milk and making Y cappuccinos uses Y cups of milk, total milk used is 2x plus Y. With only 18 cups available, the total can't go beyond 18. For time, each latte takes 3 minutes and each cappuccino takes 4 minutes, so the total is 3x plus 4y. And this has to fit within 48 minutes. Now we go back to our question. How many of each drink can you actually make without running out of these resources? The answer lies on the graph of this system of inequalities. We begin by graphing the milk constraint. We write it as an equation. The intercept of these lines, all the points, 0, 18, and 90. Draw the line through these points. Then we proceed by using the origin as our test point. That is, substituting x equals 0 and y equals 0 to the milk constraint gives us 0 less than or equal to 8, which is true. Then shade the side containing the origin. Now let's put that one aside. Graphing the time constraint may proceed similarly. We write as an equation, intercepts are 0, 12, and 16, 0. Draw the line, use the origin as a test point. 0 is less than or equal to 48. True again. So we shade the side at the origin. Combining these two graphs gives us the graph of the system. The overlap of these two shaded areas is the feasible region. This region represents all possible combinations of the two drinks. For example, 5 lattes and 5 cappuccinos. That's it. Now, let's make it more complicated. Say you have 10 loyal customers and expect at least 10 cups during the rush. They don't really mind which one the barista recommends. So this changes the picture because it sets a minimum instead of a maximum. We proceed in a similar manner to obtain the graph of x plus y greater than or equal to 10. This time the shaded region is away from the origin since testing the origin gives us 0 greater than or equal to 10, which is absurd. Also, we can verify that, for example, a random point, say 9, 3, it's on the shaded region. Why? Substituting 9 plus 3 is equal to 12 greater than or equal to 10. This is true, so 9, 3 lies on the feasible region. Unlike earlier inequalities where the origin often worked, the feasible area is now pushed away from the origin. Now, the overlap is bounded by 3 inequalities. It forms a triangle, but one corner has a negative x. which makes no sense in reality. We'll fix that. Of course, you can't make negative number of drinks. So, we only look at non-negative numbers of lattes and cappuccinos. With these, that is, the visible region is trimmed down to the first quadrant. The polygon now has corners at 0 and 10, 8 and 2, 4.8 and 8.4, and 0 and 12. These are the realistic combinations of lattes and cappuccinos that satisfy milk limits, time limits, customer demand, the common sense rule of the negativity. Now, there are other things that we should consider here. For example, the solution 4.8 and 8.4. Of course, there are no lattes that are 4.8 cups and cappuccinos that are 8.4 cups. We can limit ourselves to this for now. Systems of inequalities don't just tell you how many cups to make, they lay out the full cafe menus of choices. The next video will talk about a natural question to ask. Among the solutions, which one is the best?